Okay, now, so retrospecting what we've already known regarding the position, no? So we have a function, no? An equation that represents the position of our forward mechanism. So actually, if you find the derivative of that position equation, so knowing that the derivative of position is the velocity, after finding the derivative of that equation, we can actually find the velocity, no? Or the velocity representation of that position if that's interesting. So if you want to find also the next derivative, then you will get the acceleration. No? So well, let's not get ahead too much, but let's first discuss the velocity. So the linear velocity, for example, is just the derivative with position over time, no? And that is, well, in our example, before. So R here is the position, the radius. So how much does this position changes? It is dependent upon the the angle, no? Actually, it is also dependent on the angle sometimes. So the velocity, this linear velocity is also equal to the radius times the angular velocity omega. So the velocity omega naman is the derivative or the change in angle over time. So we have d theta over dt, no? So another thing for sign convention, no, kasi it might be the velocity might be positive or negative depending on the rotation, no, or the angle of rotation. So if your angle is sorry, yes, if your angular velocity is negative, that basically means it is revolving clockwise, no? If it is positive, it is revolving counterclockwise. Okay, so let's move on to the next slide. Why is it not moving? Okay, so now let's discuss the relative velocity, because in this four-bar mechanism, um, there are two, no, positions in relative to each other that can be moving. So if you can imagine your four-bar mechanism is something like this, right? Okay. So if this is rotating in this position, so it can be measured directly. No, it is easy to measure this velocity right here, right? But the problem here is if you want to measure the velocity at this point, knowing this velocity right here, no, it is actually hard to find because it is in reference with two constraints, no? So you have this point here and you also have this point here. So if this is moving, no, let's say in this in this relative rotation, no, so let's say it might be rotating that way or maybe rotating this way, okay, because this is a circle, right? So what happens is it is also constrained by this rotation right here. So in other words, we need to find the relative velocities, of this point so that we can pinpoint kung ano ba talaga yung velocity nitong point na to. So you can imagine another scenario here wherein if you have you have this straight rod right here, no? You just have a hinge here and then you have a straight rod here. So if this is not moving, no? Well, parang naglag. Why is it lagging? And okay, sorry about that. So for example, this is not moving, no? This is not moving. Only this one is moving, no? So due to, let's say, gravity, it moves to this way, no? So we don't have really a problem with that. It is easy. The velocity can be easily measured. But the problem is, what if this frame here itself is also moving? So this is moving. You're also rotating this way, no? In this direction. So how do you now define the velocity, no? So there is a way to do that, which is called the relative velocity. So this scenario here and this scenario and this joint here is also the same. no? So this point here, this we can assume that this is the frame which is moving, and this is also rotating in this way or this way, no? So the actual velocity here is in relative to this point as well, no? Okay. So therefore, for this example, if you have your hinge here, if you have your hinge here, and this is moving at velocity a, va, and it is trying to rotate at vpa, no? So therefore, their relative velocity will be the difference of these two velocities, no? Actually, they should be vectors, no? It is not really shown here, but it is in boldface, no? Just remember kapag naka boldface or may sign dito na ganyan, it means vector. So the difference in their vectors, no, vector velocity will be their relative velocity. In the textbook, they actually call this the velocity difference instead of the relative velocity. They are distinct. The relative velocity and velocity difference are actually different terms. But for now, since we are only talking about basics, let's just use this interchangeably. No? Wala naman tayo paggagamitan ng ibang relative velocity. Well, that's it. So, um, if again, no, going back to the velocity analysis itself, how do we now find the relative, not really relative, but the velocities of our points here, no? So if this is rotating here at this direction, what is this velocity here, no? So how do we know that? And what will be the rotational velocity as well of this? No? So there are different, there is a way, no? There's no different, but there is a way to solve for the or represent this velocity by just finding the derivative, no? Finding the derivative of this equation that we've built up recently. So if you find the derivative with respect to time, no? So we have this equation, okay? So e raised to j theta is very easy to derive, no? If you can remember. So this will be the derivative. And then using the chain rule, you have to multiply this by the derivative of theta 2 over dt. Same goes for the other terms. So we have this. So we know that theta 1 is equal to 0. So we can just cancel this out. So it is not changing, no, the angle theta 1. And if we make things a bit more compact, so we know already that the angular velocity is also the same as d theta over dt. So let's just represent this in this much more compact version na mas maikli. So we have this equation, and then we expand this again, no, using the Euler identity, no, for polar to Cartesian. So you have this. Okay, so simplifying this, since we have two j's, we can substitute. Oh, sorry, we can distribute the j's here. So this will be j squared, and we know that j squared, no, in complex numbers, if you have I is equal to I squared, right? It's equal to -1 and so on. So I3 is negative I, and I to the 4 is 1. Okay, so basically this is the same thing as I and j, no? Whether you use I or j as notation for complex numbers. Okay, simplifying this, the sign will be negative, no? And so on, no? Okay. So having this, we can separate the imaginary and the real constants, no? So again, what we are doing here is the equating of coefficients kasi yan, guys, no? So, yung 0 kasi dito, it could also mean 0 plus 0 I, know, if you can remember in your partial fractions. It is often used um, in that application, no? So, 0 plus 0 I. So, lahat ng 0, equate nyo sa real. Ito yung mga real. And then, lahat ng imaginary, equate nyo rin sa 0, no? Okay, so we have this already. So, if we solve this again with the same method, no, or strategy that we've already done before, so we can solve for the angular velocities, no? Okay, omega 3 and omega 4. Okay, so given you know the omega 2, so the angular velocity of this link 2, no? And also the lengths, of course, the lengths are given, and the angles theta 4, theta 2, theta 3, and theta 4, then you can solve for the instantaneous. This is actually the instantaneous angular velocity omega 3. Okay? So in order to find the angular velocities, you need to first find theta 3 and theta 4. So sorry guys, pero um, you really have to remember a lot of this, no? So this is only applicable, no? Yung mga sinasolve natin, only applicable for 4-bar mechanisms. Na simple lang, no? I won't get into too much detail kapag sa mga quick return, no? So dalawa lang solve natin. We will only solve a 4-bar and the slider crank, no? So because as you can see, this is very simple, no? 4-bar mechanism is very simple, but the equation that is used to solve it using an exact, no, analytical method is quite tedious, no? Quite long, no, to solve. So we'll only focus on this two for the velocity analysis. Same goes for acceleration analysis in the future. Okay, so if you want to now solve for the linear velocities, no, at let's say at point B, so if this is rotating at this direction, so you have a linear velocity at this point, no? You have some linear velocity at this point as well, for example, for this point, no? So you have here a way to solve that one. No? So you can find VB, VC, and VCB by just multiplying the radius or the length of the link times its angular velocity. Okay, so there are two ways to solve for VCB. So VCB guys is this one, no? So the angular velocity, or not really the angular velocity, but the linear velocity of link 3. So if this is rotating here, it will kind of rotate at this, or it will have a velocity at this point, no, pointing to that direction. So I think it's best to just use this, no. But if you want to use this, it's fine, no. But it will actually take a little bit longer, no. So I'll just use this tree here. So for its angular velocity, you can find its linear velocity. Okay, for a slider crank mechanism, if you use the same strategy, you also have a formula, no, to solve for that one. So we want to, let's say, find the velocity VB. That's basically the formula, and then VCB and VC. We solve for that. Okay. So I think that's it for velocity analysis.